Hey everyone, I'd like to do a couple more examples of computing Galois groups. So let's just get started. The first one we're going to do is, so here we go. So let's compute the Galois group. I'm going to put a little q here. So the Galois group of the polynomial f, where f is the polynomial x to the fourth minus 2. Remember, when I put a little q here, what we're doing is we want the Galois group of the splitting field of the polynomial over q, right? That's what that little sub q means. Okay, so let's see what we have. The roots of the polynomial f are, so who are they going to be? They're going to be the fourth plus or minus the fourth root of 2 and plus or minus the fourth root of 2I. And so they are plus or minus 2 to the 1/4 and plus or minus I to the 1/4. And so what does that tell us then? Well, an easy way to think about who the, or an easy way to see who the splitting field is, right? So we can say, so sigma, the splitting field, is going to be q adjoin. Well, okay, officially it's adjoin all 4 of those roots, but we don't need the plus or minuses. And if I join 2 to the 1/4 and I times 2 to the 1/4, that's the same as adjoining just I. And so one way to think of it, in fact, let me write it this way. So it's 2 to the 1/4 comma I times 2 to the 1/4, which is equal to q 2 to the 1/4 comma I. Nope, that should be a comma there. Okay. And so this makes it easy to compute the degree. So since this extension sigma over q is Galois, why is that? Well, it's a normal extension because it's the splitting field of this polynomial over q. It's separable because q has characteristic 0. Every extension over a field of characteristic 0 has or is separable, and of course it's also finite because because it is. So q is the Galois. So what this tells us is that the degree of the extension is going to match the order of the Galois group. So since it's Galois, we have that the order of the Galois group is equal to the degree of the extension, sigma over q. And then you can just tower lot to compute this. So this is equal to the degree of sigma over q adjoin fourth root of 2. I think that's the order I want to do it. Oh, no, actually do it the other direction. So I join I here. So this is q adjoin I, and then this would be q adjoin I over q. And you know what? Let me just write it out. I'm being a little bit lazy there. So this is really, let's write it like this. Q adjoin 2 to the 1/4 comma I over q adjoin I. Hopefully it's clear that this extension has degree 4, right? The minimal polynomial for 2 to the 1/4 over q adjoin I is going to be the same polynomial right there. So this has degree 4. And then this will be q adjoin I over q, right? The degree of this extension definitely is equal to 2. The minimal polynomial of I over q is x squared plus 1. So what do we have? This is equal to 4 times 2, which equals 8. And so we know that the order of our Galois group is equal to 8. All right, well, how many possibilities we have then? So the options for the Galois group of F, well, it could be Z8, it could be Z2 plus Z4, it could be Z2 plus Z2 plus Z2. Those are the abelian choices. There are also two non-abelian groups of order 8. One of them is D4, right, the dihedral group, and the other one, we'll write it as a Q, the quaternion group, right? That's the other non-abelian group of order 8. I think in Math 481 we talked about the quaternion group. It was a homework problem, and it can be represented in terms of matrices. The way to distinguish these, or at least what we will need to distinguish these, is you can just talk about the orders of elements. And so the group of quaternions has 6 groups of order 4. Sorry, 6 elements of order 4, right? Where D4 has 1, 2, 3. It just has 3 elements of order 4. So there's our 5 choices. And so the goal now, what I'd like to do is figure out who the Galois group is. It's going to be isomorphic to one of those 5 groups on our list right here. And so let's figure out who it is. Now, a basis for Q adjoint I over Q, that's just going to be 1 and I. And a basis for Q adjoint 2 to the 1/4 comma I over Q adjoint I is still going to be, so it's going to be ascending powers of 2 to the 1/4. So that would be 1, 2 to the 1/4, 2 to the 1/2, and 2 to the 3/4. So the basis for Q adjoint 2 to the 1/4 comma I over Q is going to be all possible products that you can make from these two bases right here. So this will be 1 comma I, 2 to the 1/4 comma I times 2 to the 1/4, 2 to the 1/2 comma I times 2 to the 1/2, 2 to the 3/4, and I times 2 to the 3/4. So what do I got them all? 1, 2, 3, 4, 5, 6, 7, 8. Yeah, okay, so there's our basis. And so from this, we can see that any element of the Galois group then will be completely determined by what happens to 2 to the 1/4 and I, right? If you know what happens to those via the automorphism, then you can figure out what happens to any element of the basis, which then allows you to know what happens to any element in the splitting field. So any element of gamma of F is completely determined by the images of 2 to the 1/4 and I. Now, so if sigma is in gamma of F, then what do we know? Well, gamma of F, any element of gamma of F, has to permute the roots of the polynomial that we're working with, right? So, so any element, let's say it like this. So then sigma permutes the roots of f. So what that means is that sigma of 2 to the 1/4 has to live in the set 2 to the 1/4. I guess it's really plus or minus 2 to the 1/4. Plus or minus 2 to the 1/4. And plus or minus I times 2 to the 1/4. Also, okay, so that tells us something about the images, the potential images here, but we also need to know what happens to I. So we'll say also, Q adjoint 2 to the 1/4, comma, I is the splitting field of the minimal polynomial for I, so the splitting field of x squared plus 1 over Q adjoin 2 to the 1/4. Okay, so what does that tell us then? It tells us that if we have an automorphism of our splitting field for the original polynomial that fixes Q adjoin 2 to the 1/4, then it has to permute the roots of x squared plus 1. And say, so if sigma in gamma of f, so that means it's an automorphism of Q adjoin 2 to the 1/4 and I, fixes Q adjoin 2 to the 1/4, right, then sigma of I has to be in the set plus or minus I, right? So this gives us a handle, by thinking in this way, it gives us a handle on what has to happen to 2 to the 1/4. It also has to tell us what happens to sigma of I, given that it fixes the elements of Q adjoin 2 to the 1/4. So, yeah, let me look at. So from this, or I'm going to use this information, and I would like to define a couple of elements of my group. So let's define. So I'm going to call them sigma and tau. So first, let's define sigma. So let's define sigma from Q adjoin 2 to the 1/4 I to Q adjoin 2 to the 1/4 comma I by sigma of, remember, what we need to know is what happens to 2 to the 1/4 and I. So sigma takes 2 to the 1/4 to I times 2 to the 1/4, and it takes sigma of I to I. And I'm going to define tau also Q adjoin 2 to the 1/4 I to Q adjoin 2 to the 1/4 comma I by tau of 2 to the 1/4, and here I'm going to send it to 2 to the 1/4, and by the work we just did before then, right, tau will have to take I to either plus or minus I, and I want this to not be the identity, so this is going to be tau of I equals minus I. All right. Now, I'll say check, that this list right here, so it's going to be the identity, sigma, tau, sigma, yeah, let's do the sigmas first. So sigma squared, sigma cubed. You can check pretty quickly that sigma is an element of order 4. And then tau, I'm going to multiply okay, sigma tau, tau sigma, and sigma squared tau. This is a complete list of automorphisms of gamma of f. So this is, I just need to say, is equal to gamma of f. Now, what exactly am I saying here? Well, we know that the group has 8 elements. And so if you can verify that all 8 of these are different elements, they are definitely elements inside gamma of f. And so if you've got 8 of them and they're distinct, then this has to equal all of gamma of f. So now, in particular, sigma tau is not equal to tau sigma. Okay, so that tells us that it's a non-abelian group, which means we can cross those first 3, the abelian choices, off the list. So this group here has to be equal to either, or isomorphic to either D4 or Q. Now, you can do this, so now it just amounts to computing orders of elements. So compute orders of elements. Let me just make a little table here. So the possible orders here, 1, 2, and 4. It's not cyclic, so those are the only possible orders that it has. And it turns out then that if you actually crank this out, the identity has order 1. Sigma squared tau, sigma tau, and tau sigma. Oh, wait, what? One, two, three, four. Oh, right, sorry. Tau sigma and sigma squared tau have order 2. And then I think now I just realized I said something weird. Dihedral group has 2 elements of order 4, not 3. Elements of order 4 are, who's left here? Sigma and sigma cubed. Because we only have 2 elements of order 4, this has to be the dihedral group, not the quaternions, right? So conclusion is that gamma of f is isomorphic to D4. You're going to need to know this for a homework problem. I'm actually going to now work out the subgroup lattices. If you turn to any algebra book, I mean, you'll be able to figure out who the subgroups are, or it'll list the subgroups of D4. So D4 has 9 subgroups, 9 proper subgroups. So 9. Subgroups. There are 5 subgroups of order 2. Right, 1 corresponding to each. What's wrong here? 1, 2, 3, 4, 5, 6. Oh, sorry, that should say sigma squared times tau. So there are 5 subgroups of order 2, 1 for each of the elements of order 2. There is 1 subgroup of order 4. 1 cyclic subgroup of order 4. Yeah, 1 cyclic subgroup. And then there are 2 subgroups that are isomorphic to the Klein 4 group. I'm going to call these capital A and capital B. So A, which is the identity sigma, sigma squared tau and sigma squared tau. And then B, which is 1 sigma squared sigma tau and tau sigma. Okay, so both of these are isomorphic to Z2 plus Z2. Also, so we'll say of these, some are normal, some are not. So of these AB, so of these A, B, subgroup generated by sigma, subgroup generated by sigma squared, the identity and the whole group are normal subgroups of the Galois group. Okay, so now what I'd like to do is draw the corresponding lattices. And so I'm going to draw the subgroup lattice. And by the way, I just got this out of a book, right? I mean, I don't have the subgroup lattice for D4 memorized. And I don't expect you to either, right? So you're more than welcome to look up this kind of thing in a book or on Google it and you'll find it. Okay, so at the top we've got the trivial subgroup. Now I'm going to be writing down the subgroups of order 2 here. So we're going to have 5. Let me make this a little more symmetric. In the middle, I want the subgroup generated by sigma squared. Then we have sigma tau. And tau sigma. So here are 5 cyclic subgroups of order 2. Then below, we have sigma, and then we have A, and we have B. And 1, 2, 3, boom, 1, 2, 3, and then at the very bottom we have gamma of F. Now, computing fixed fields can be kind of a pain. Actually cranking these out by hand. So I encourage you to do a few of these on your homework problem, and then it's fine to look it up. It's a little bit on the tedious side. So I'm going to draw the corresponding lattice now. I2 to the 1/4. I2 to the 1/4. So what this is saying is that the fixed field of sigma squared tau, or the subgroup generated by sigma squared tau, is equal to Q adjoint I2 to the 1/4. Then we get Q adjoint 2 to the 1/4. Q adjoint 2 to the 1/4. Right in the middle, we have Q adjoint I and square root of 2. And then we're going to get the other two, 1 plus I. So Q adjoin 1 plus I times 2 to the 1/4. And then over here we get Q adjoin 1 minus I adjoin 2 to the 1/4. Right? So these are the fixed fields corresponding to this first row right there. Then we're going to get Q adjoin square root of 2, Q adjoin I, and Q adjoin I root 2. And then at the bottom, corresponding right to the fixed field, who fixes everybody? Well, it's the whole group. Sorry, who fixes Q? The whole group. And then there we go. Now, maybe I made this look a little bit too easy, right? To figure out, for example, who this fixed field is, the fixed field corresponding to A, I would need to set up the equation by expressing a generic element in terms of the basis. There's going to be 8 elements. I would have to use, so let's see, I can't remember exactly who lived in A. I think it was the identity, sigma squared tau. Oh, actually, probably tell me right here. Sigma squared tau and sigma squared tau. Right, so those 3 elements I need to multiply by that generic element, see what happens, set it equal to that original generic element, solve the equations to figure out, oh, the elements that are fixed are going to be those of the form A plus B. It'll probably look like this, 2 to the 1/2 is the way I was writing it, right? So you'd find that these are the elements that are fixed by every single element in capital A. That's how you would identify that it's Q adjoin square root of 2. All right, and you have to do that for each one of those. Of course, for the smaller groups, it's much easier. As the groups get bigger, then there's more computations to do to actually find these. Okay, so let's do another example. We have not done an example computing over a field, a Galois group of a field that's other than Q, I don't think. And so now, let's do an example where the base field, the field of coefficients, is not the rational numbers. So for my next example, I want to compute the Galois group of F over Z3, where F is exactly the same polynomial we had before, x to the 4th minus 2, which, by the way, in Z3, that's equal to x to the 4th plus 1, right? Minus 2 is the same as plus 1. I'm sure you can guess why you can't see me. That's why. I was just grabbing myself a drink. Boo. Sorry. Okay. Now the first thing to recognize for this polynomial right here, so let's note that if we're working over Z3, this polynomial is actually reducible. So it's equal to x squared plus x plus 2 times x squared minus x plus 2. So this is happening in Z3 bracket x. So I'm going to call this polynomial G and this one F. So let's write G equal to x squared plus x plus 2 and H equal to x squared minus x plus 2. Now, what I'm trying to do, I'd like to find, I need to figure out who the splitting field is. And so I'm going to do that by applying Kronecker. So if we apply Kronecker, So letting, say, alpha equal x plus the ideal generated by G, we have Z3 adjoint alpha, which is of course isomorphic to Z3 bracket x mod the ideal generated by G. Oh, I should point out that these polynomials are, each of these is irreducible over Z3. So anyways, this extension right here contains a root of, well, G or F, whichever you like. So now, the elements of Z3 adjoint alpha, or let's just say who this is, I don't need to say elements. So Z3 adjoint alpha consists of the following elements. So we're going to have 0 and 1, and 2, of course. So 0, 1, 2, it's going to have alpha, alpha plus 1, alpha plus 2. And then, what else do we have? Oh, 2 alpha plus 1, and 2 alpha plus 2. 2 alpha plus 1, 2 alpha plus 2. Also, we can say and alpha squared plus alpha plus 2 plus alpha plus 2 equals 0. So alpha squared is equal to, well, it's minus alpha minus 2, which is the same as 2 alpha plus 1. All right, so we need that fact right there. So the roots of G now, there are 2 of them. One of them is alpha, and the other one turns out to be 2 alpha plus 2. So alpha and 2 alpha plus 2. So this extension right here, Z3 adjoint alpha, contains all the roots of G. It turns out that it also contains all the roots of H. So, so we could say also check. So also, the roots of H are, they turn out to be alpha plus 1 and 2 alpha. Alpha plus 1 and 2 alpha. So that's nice. We don't need to extend any further, right? We have the splitting field for, I hate this, just looks so ugly. I gotta fix this. Gamma sub Z3 of F. Okay, so Z3 adjoint alpha is the splitting field for x to the 4th minus 2. By just adding that single root right there, right, we got all the roots of F. All right, so we can say, so Z3 adjoint alpha is the splitting field for F over Z3. Notice that our polynomial has distinct roots, right? 4 distinct roots, which means that we have separability. So since F is separable over Z3. The extension Z3, Z3 adjoint alpha over Z3 is Galois, right? It's a finite extension. It's normal because of the splitting field. Now we have a separable. That tells us that we've got a Galois extension. And so what does that tell us? It tells us that the degree of the extension matches the order of the Galois group. Now, what is the degree of the extension? Well, we adjoined the root of a degree 2 polynomial, which means the degree of the extension is 2. So since, okay, so we can say therefore, the degree or the order of the Galois group is equal to the degree of the extension, the minimal polynomial for alpha over Z3 has degree 2, and so this is equal to 2. So the Galois group is a degree, or is a group of order 2, which means it's isomorphic to Z2. So the non-trivial element of gamma of F is defined by taking, where'd my roots go? Oh, by taking alpha to 2 alpha plus 2. 2 alpha plus 2? Yeah. So it is defined by, right, it's got to permute the roots, and so it's got to permute the roots of G, and so it's got to be take alpha to 2 alpha plus 2. The subgroup lattice and corresponding lattice of intermediate fields is not very interesting. All right, there's the subgroup lattice. And then flip it over, we've got Z3 adjoint alpha over Z3. I want to take another look at the previous example I did. I mean, this in the end is actually kind of an easy example. Let's look at the previous example. And so, I don't know, let's just say like this. So let's return to the previous example, where we were looking at the polynomial x to the 4th minus 2 viewed as a polynomial with coefficients in Q. Now, so let's say letting alpha equal 2 to the 1/4 and beta equal to I 2 to the 1/4, we have the roots of x to the 4th minus 2 are, so this, let's write it as a set, plus or minus alpha and plus or minus beta. And remember what I did last time? I wrote, we can say thus, the splitting field. If you remember what I did last time, I joined 2 to the 1/4 and I. And that has both advantages and disadvantages. So another way to think of the splitting field is just to say, well, all we need to do is to join alpha and beta. In which case, so let's say it like this, and here's the reason, is that it sort of allows me for a more geometric way of thinking about who the group was. Because we know that our group has to permute, our Galois group has to permute the roots of this polynomial right here. So alpha, beta, plus or minus alpha, beta, or plus or minus alpha and plus or minus beta have to get interchanged. And so, say it like this, we know that gamma of f has to be, right, it permutes the root, so it's got to be isomorphic to a subgroup of S4, and since f is irreducible over Q, right, gamma of f has to act transitively on the set of roots. In fact, let's call this capital R here. Right, it has to, so gamma of f acts transitively on capital R. So there has to be an element that takes alpha to minus beta. There has to be an element that takes beta to alpha. Now, so I'm doing this differently in the following sense. So, sorry, I forgot to draw my picture here. So this is 2 to the 1/4 right here. Over here is minus 2 to the 1/4. This is I times 2 to the 1/4. And this is minus I times 2 to the 1/4. You can draw this little diamond-shaped thing and get a feel for how the elements of the Galois group behaves, right? So I want to keep this diagram up here. Now, the degree of Q adjoint alpha over Q is equal to 4. The degree of Q adjoint alpha beta over Q adjoint alpha is equal to 2. Why is that? Well, the minimal polynomial, so the reason is that the minimal polynomial, who did I adjoin? I adjoined beta at this stage. So the minimal polynomial for beta over Q adjoint alpha is equal to x squared plus square root of 2. So what we have is we have the basis, so we've got a basis. In the first case, that's going to be 1 alpha, alpha squared, alpha to the 4th. That's the basis for this one. The basis for the second one is going to be 1 and beta, which means that a basis for Q adjoin alpha and beta for all of sigma over Q is given by 1 alpha, alpha, that should be an alpha cubed there. Alpha squared, alpha cubed, beta, alpha beta, alpha squared beta, and alpha cubed beta. Okay, so now every element, so let's say it like this, any element sigma in gamma of f is determined by sigma of alpha and sigma of beta. So what I've done, I've chosen a different basis. All right, and this basis is somehow more closely connected, in fact, it's very directly connected with the roots of the polynomial. And so sometimes it's easier, in fact, I guess I find it easier to figure out who the elements of my Galois group are, right, by choosing a basis that directly involves the roots, right? And the last one I had I, which is not quite a root. Remember, this is alpha, that's beta, and now let's think in terms of dihedral group, right? We knew that the answer in the end is the dihedral group, right? Call that one sigma. What does it do? It takes alpha to beta. And then let's call the flip about this line right there, let's call that one tau. And so what does that do? It leaves alpha and minus alpha fixed, and it takes beta. To minus beta. So once you have that, right, here's our generators for our group. Every element can be expressed as a product like that. So this approach gives you a little bit more geometric intuition for who, how to define the elements of your group right here, right? So, I mean, either one gets you to the same place, but sometimes you can think of it, maybe it's easier or more, I don't know, more intuitive maybe to think in terms of an extension that involves directly identifying the roots or adjoining the roots, and then building up your Galois group from there. Okay, so that's a good place to stop. We'll see you next time.